not there? The white one. Ah, you can take this one. Yeah, maybe. There was always another one. Maybe it might be. Just let me check. Okay. Huh? Abhishek has it. That's the one I was looking for. Thank you. Okay, I start. So, welcome to the fourth lecture. The last one that I will do systematically on the board. I think tomorrow I will go to slides to finish, at least to show you how to get where I wanted to get, and also to show you some plots of results on different models. So we started yesterday the second part on macroscopic stochastic thermo, but I started mixing it with the third part, which are applications, by introducing some of the models that are described by a density. This is the starting point of stochastic thermodynamics for systems where you want to take a macroscopic limit. And I was talking yesterday about the non-equilibrium Potts model. Where I told you that we had a bunch of units. I will draw the three-state ones driven by a force. And we have a collection of n of them. And there is an attractive force. All of the units in the same state like to be together. And I told you that in the macroscopic limit, this system, when the number of units is large enough, displays some synchronization. I sketched briefly a phase diagram where here was the force, and here was the coupling between the units. And at zero force, there are two phases. At high temperature, there's a beta here. High temperature compared to the interaction strengths, every unit is with equal probability in state 1, state 2, or state 3. But as you go to a lower temperature, it's like the Curie-Weiss model that was discussed by Bruno yesterday. You go to one of the three states. Okay, instead of 2 for the Curie-Weiss, here it's 3. So in this region, there are 3 fixed points. In this one, there's 1 fixed point, which is equal to 1/3, 1/3, 1/3 for the population. And eventually, at finite force, there's a synchronization region. And this means that if you look at the populations of these units in time, you will see that at a certain time, the probability to find all of them, the occupation concentrates on high probability to find all of them then later on there, then later on there, then like this, like this, like this. So the density oscillates. And this is, I will show you more plots tomorrow on that. So it's a rich model. And since we know how to do stochastic thermodynamics for this, I showed you how to write the rates for this in terms of density, we can also study the energetics of that model now. I think that's the important point. And that was actually my original interest, was to see, okay, can we say something about the energetics of synchronization? So this is the synchronized. Here, multi-stability. And here, I put 1/3 for the probability to be equal. There's only one fixed point. And just because I promised some references, so the first work was on the 3-state unit with my PhD, Herpisch, my postdoc, Tigna, and myself in PRX. And it was also limited, this work, to Arrhenius rates. But we did the detailed analysis of stochastic thermodynamics going from the microscopic level of description, where one specifies the state of every unit, to the mesoscopic and to the deterministic level. Then, still with Herpisch, with another PhD students of mine, Cossetto, and with Gianmaria Falasco, in the Journal of Physics 22, we looked at fluctuation, macroscopic fluctuations in this class of systems of Potts model. Not 2020. So this is macroscopic fluctuation. And more recently, with my postdoc, I mean, now he's in Berlin, but Maibaum and myself, this is on arXiv. It has been accepted in PRE, but I give you that. It's not yet published. So in these studies, what is interesting is that we could really do a very general analysis of this Potts model that I described for any Q states and for any class of, I mean, a very broad class of rates. And we could explicitly construct the limit cycles near the synchronization, near the bifurcation. So there's a Hopf bifurcation that creates this limit cycle in the deterministic dynamics that gives rise to this oscillation. And close to the synchronization, so not too far away from it, but close to the synchronization, we could explicitly construct it for all of this class of systems and study the dissipation on this limit cycle, and prove that the dissipation always decreases. The dissipation per unit, that's the meaningful quantity, right? You take the global dissipation per unit, you divide it per unit, and you show that we show that the dissipation per unit decreases as you go into the synchronization threshold. We observe this numerically here, but this is a general proof for any rates and any Q units. And we also have complex analysis of the phase diagrams. I mean, this made me also realize how still analytical approaches are crucial, because we studied that model numerically before, but this model is already so rich, it has so many different behaviors that if one studies it analytically, one sees a lot of things that one is almost, without knowing that they are there numerically, one would never discover them. So it requires a lot of work because these are complex, complicated nonlinear systems, but already a model that is relatively simple to formulate like that is extremely rich. I will show you some phase diagrams to give you an idea of how complex things can become. because some system, if Q is odd, so if the number of units is odd, synchronize. If it's even, it doesn't synchronize. You can have multiple limit cycles, so it's pretty rich. Okay, so that's one big class. I showed you a specific class because it is always these circles. The energy of each site is assumed to be constant. You could have energy profiles, but then most of our analytical analysis is based on the invariance under rotation of the system. So it would be much harder to analyze. But this gives you a flavor that certainly one class of model where you can apply this macroscopic limit of stochastic thermodynamics is models where you have n units that interact with each other. Good. Now I go to the second class, which are chemical reaction networks. This obviously is also a very important, for short, CRNs. This is also a very important class of systems for biology, obviously. And the way I just want to give you an idea of, again, how one writes the rates for these systems and how one connects to the rates I was giving you and the local detail balance I was giving you in terms of density, so that you understand that, yeah, that's the starting point, and then it's a matter of applying stochastic thermodynamics to these kind of systems to study their energetics. So the way it works is like that. A formal way to write a reaction with species Y, which will denote the chemostated species that you should think of as the reservoir species. So I introduce these coefficients that are the stoichiometric coefficients of a reaction. This is the symbol of the species, the big Y. So this is telling me that there are different species big Y, I sum over them, multiplied by a certain stoichiometric coefficient, plus the species I. These are the non-chemostated species. These are the ones that are potentially in small number or in smaller number. Their symbol is X, I, and the reaction is rho and minus rho, and it goes to sum over I. The stoichiometric coefficient for the backward reaction is minus rho X I plus the Y species mu Y minus rho. So maybe we can right away give the example. This is really a toy model, but that is popular in the physics community. It's the Schlegel model. So it's like this. 2x plus a gives 3x with rate k1, k minus 1. And then there's a second reaction. B gives x with a rate k2, k minus 2. And now A and B are my Y species. So I should say this is A and B, because I assume that these are the ones that are fixed from the outside. And X here, there's only one species. Xi is there's only one component. It's X. Okay? So the picture that you can have in mind, if you want to see it in terms of reservoir, you can imagine that I create, this is in a box, in a container, in a solution. Yeah, it needs to be a solution. It could be a gas too. And whenever X, this reaction happens in this direction or this direction, B gets consumed or produced, there's like a mechanism that from the outside resets its concentration. Okay, so you can think of this as a bath, so with a chemical potential B, and same thing for A. In such a way that the concentration of A and B never changes. Okay? Now, a very simple practical way to do that is to put A and B in very large concentration so that you can neglect the, if you have millions of molecules and you remove one, you're not going to change much the chemical potential of that species, but X is in much smaller number, and so X you want to describe stochastically. But another way is really to think of it as there's a control from the outside, a bath coupled to it, and so because the chemical potential here is fixed, it always keeps this concentration at a given value. Yes?
What's the last term in the reaction?
Yeah, I forgot to put the Y. Sorry. Okay, so let's look indeed at, where did I write this? So now, first I define the object, which is the stoichiometric matrix. Oops, this is my delta, the delta that we introduced when doing the stochastic thermodynamics in terms of density. I define it as the difference of these stoichiometric coefficients, okay? And so the indices here, it's a vector which will have component y and x. So let's look at the Schlegel model and let's write delta. So the reactions, let me also say, yeah, reaction 1, reaction 2. So 1 and 2, these are the reactions. And then the species, so we put X, we put A, and we put B. So what does, the philosophy is always the same, huh? But I think it's good to see in different contexts how it works. So reaction 1 in the positive direction removes 1x, removes 2x, produces 3x, okay? What did I do in my notes? No, yeah, it's correct, because it's the difference between the two. So it consumes 1, produces 3, so the net effect is 1 on X. It produces 1X. And it consumes 1A. I did something wrong in my notes, I think. Yes, this is wrong. Okay, it's a 0. I think this is correct. Yes?
This limit where the concentration of A and B usage doesn't change. So I can just forget them and just write down the dynamics for X, I guess.
Exactly. So that's going to be the point, is that the stochastic process will only be on X here. And A and B, they are not dynamical variable. They are fixed, and they can be absorbed in the rates at the level of the description. Yes. Yes, so this is correct. The net effect is this. I simply did it wrong in my notes. And reaction 2 takes out 1b, minus 1, and produces 1x plus 1, 0. Okay, so that would be the stoichiometric matrix of this reaction network. Now there's a general form that we can give to the rates. It's called mass action kinetics. So the rate of a reaction rho starting from a given vector n. And now n is, in general, a vector. In this case, it's only x, because it's going to be only the internal species. So it's the volume multiplying the, times the rate constant k rho times the products over all the internal species. So again, it's x here. Volume times the stoichiometric coefficient of the products, ni factorial divided by ni minus the stoichiometric coefficient with the, and then there's the concentrations of the y species to the power of the stoichiometric coefficient of the y species. So what are we saying here? We're saying that, and we will actually do it for this model, we're saying that the flux, the probability to go through this reaction in this direction, for the x part, this is what we expect. I don't know if you're familiar with standard chemistry rate equations. It's simply the stoichiometric coefficient of the deterministic species, because that's as I said, it's a fixed concentration. It's not a stochastic variable. So it's the concentration of A to the power of its exponent, which is 1. But here, for the stochastic species, we have, that's actually a trick to write it, because what's happening here, you see this ratio, for every species that does not enter the reaction, is going to be 1. So the ratio is only non-zero for the species that enter the reaction. And for if you have a species that enters with a stoichiometry 1, you basically get the number of molecule of that species. But if it enters twice, you will get the number of molecules times the number of molecules minus 1, because the probability that an event happen is proportional to the number of molecule times the number of molecule minus 1, because 1 is already gone. Okay, so let's do it for the Schlegel model. So R1 I can write it as x is k1 over v. So let me write it and then we check. A x minus 1. So A is this part, okay? That's the simple part. Stoichiometric coefficient of A is 1, so A to the power 1. K1 is the K of the reaction. Now, the volume is related to this. So species X, so we have, it's consumed twice, right? The stoichiometric coefficient of the reactant, this is 2. So it's concentration of X, well, it's X factorial divided by X minus 2 factorial. So X times X minus 1, that's this term. Okay, this is the X factorial divided by X minus 2 factorial. It's equal to this. And now in terms of volume, we have 2, so V and 1 over V, 2, it's V. And so we have this, okay? And this, I think, is more intuitive, because you see that, okay, it's proportional to the concentration of A, and as I was saying, it's proportional to the square, because you need 2 molecules of X to meet, okay? But if you pick the first one, there's one less for the next probability, so that's why there's the minus 1. And so you get this. This is known as mass action law. I mean, I will not do all the rates, but you can check. For this one, you will get k minus 1 divided by v squared x minus 1 x minus 2, because now we have a stoichiometric coefficient 3. And let me write this here. R2 of x is k2b, and R minus 2 of x is k minus 2x. Okay? These ones are very simple because it's a linear reaction. Okay, so that's the general expression. Yeah.
The second case, stoichiometric coefficient, that is 3, right?
Yes. Yeah. It's 3. So in the stoichiometric matrix we had 3 minus 2, so that's why we got the 1. But the stoichiometric coefficient is this guy for the reactant, and it's this guy for the product.
So what are the C's? What are the C's? The product over y, cy. Yeah. So what exactly is that in cy?
This is the concentration of the chemostated species. So the chemostated species are A and B. I think they are there, right? So in the reaction 1, it's A that enters. No, yes, forward. I wrote forward and backward above, that's why I got it. But in the forward you have A, and then in the here you have B. Okay, so I could write it 2 here. So yeah, I actually did write it. It's this. Maybe I'm in, yeah, okay, it's true. Okay, this is the concentration of, I should have maybe specified that. This is the concentration of this with the index y. This is the symbol. This is the concentration of that symbol. Okay, so it's here and here. Yes?
This is the volume of the reaction chamber, right?
Yeah. Yeah, and that's actually the important thing for the macroscopic limit. It's with that you take a large V limit when you take a macroscopic limit.
Can you explain, physically why this 1 over v square? Why
It is, that's actually what is going to make the rate converge to mean field rates in the macroscopic limit. Because in the macroscopic limit, let's maybe show it on a concrete example. I will divide the rates by the volume, because the rate is proportional to the number of molecules. So I will define an intensive rate. When we will take the macro limit, I will explicitly scale the rates as 1 over the size to have intensive rates. And so I will get a V3. And that V3, so I will have 1 V here, 1 V here, 1 V here. And these terms will drop because of the 1 over V. I take the V infinity limit. And I will get the concentration, so X over V, to the, you see? I will get X3 over V3. That is going to go to the concentration of 3 to the power 3. And then you're back to what I actually wrote for the chemostats. So in the large V limit, when I divide, I make my rate intensive. I actually recover this. So that's the scaling with the size that is needed to have a proper macroscopic limit.
So normally when we into the concentration, we think the volume term is already included in that.
Yeah, because you see, but X is not a concentration. Huh? X is a number. So we are dealing with numbers of molecules, and it's only if I divide by the volume that I get a concentration. So this is the key difference here. This is a concentration. I should have specified that. So if you want, as I said, these are fixed numbers of, I could have been more specific, but these are fixed. And so they will be defined by a concentration. So this is the number of A per unit volume and the number of B per unit volume. Okay? Good. Now, I will not do all the things explicitly, but this, I will give you the ingredients to check it by yourself. You can, by taking, you should explicitly calculate this. This is easy. Okay. Write the expression corresponding to this. Then take the log ratio of this divided by this. Okay, this is the object, the key object for the local detail balance. I multiplied by RT. And you need to convince yourself that you can write this as a potential at N minus a potential at N plus delta N plus, the force, the non-conservative force that is given by the chemical potentials of the chemostats. Okay, so this is the form I gave you when we looked at local detail balance. We got it in traditional stochastic thermo, and I rewrote it explicitly for stochastic thermo in terms of densities. So now let me define the different quantities. This guy is the chemical potential of the chemostated species A and B in our application. And it is defined as the chemical potential, it's called the standard chemical potential. There's also a term here that contains the concentration of the solvent. It's a constant term. I put it there because it is there, and otherwise you will be confused with the volume. So this you need. Sometimes this is actually defined as mu y, a different standard, because this guy is always constant. Plus RT log of the concentration of Y. So this is a typical expression of a chemical potential. Up to this, if you think of this as you have a standard chemical potential plus RT log of the concentration. And now I need to give you the expression of phi. I should write it here. Do you mind if I move there? I'm a bit messy with the space, but okay. Hop. Now I need to define the phi of n, okay, so that you can check this explicitly, because we have the phi appearing. So you have these two expressions. You take the difference. This is easy to check. And now this guy, it is defined as the sum over I, mu I, and I, plus RT log Ni factorial. And this is the mu zero, yeah, let me, write it like this. It is mu 0 minus RT log n concentration of number of molecule in the solvent. And that NS divided by the volume is going to give you the concentration of S. Okay? So keep in mind that it's CS is going to be NS over volume. And what else do I need to tell you? I need to tell you that the connection, this is a standard for people doing chemistry, the connection between the mu zeros and the K, you need to use the fact that RT log K rho divided by K minus rho is minus the sum over I mu I 0 minus KT log concentration of S minus sum over Y delta rho Y mu Y 0 minus, sometimes I'm writing R and sometimes K. So, this is because chemists usually write R. It's simply the Avogadro numbers times K that is equal to R. So it depends on whether you use moles or molecules. If you use number of molecules, it's K. If you use number of moles, it's R. What I was saying, RT log CS. Yes, here we go. So with that, you have all the ingredients, okay? And you can check this, take the ratio, and with this definition of phi, and using the fact that the log of the ratios of the K's are given by these delta mu's, try to check that you recover this. Okay, so you see, this is, I showed you that now you can take any chemical reaction network, open chemical reaction network, and apply the stochastic thermodynamic framework to it. And that mass action law, so this expression is compatible with local detail balance. And as a historical note, I think that the chemists were the first who understood local detail balance. Because the fact that the ratio of the constants is related to the chemical potential, this is the key. And it is also directly related to the fact that the ratio of a forward flux divided by a backward flux for what they call an elementary reaction. Elementary reaction means that there are no hidden steps. So, and this we said our transition, we should not coarse grain stuff that is out of equilibrium. So the chemist language for saying that is for elementary reactions where you really resolve a reaction at the level of single collisions. This fact that the forward and backward rates were related to the thermodynamics, it goes back to the 1910, 1915. Okay, so I think it's one of the first instances where they understood that. A second one is Einstein with spontaneous, with the Einstein coefficients, spontaneous absorption, spontaneous and induced emission. The fact that he realized that you had, there was a need to introduce spontaneous emission to find a thermodynamic equilibrium. I think that's probably the second instance. So in a sense, the history of local detail balance is very old. It's simply that it's only recently that we have kind of a general formulation for it. Okay, that is for chemistry. I could, I said it in words, that if we take the macro limit, since I didn't show it at the theory level, I will not spend more time on it, but I gave you a hint of how, if you divide this by V and you take the V limit, you get macroscopic rates, and you can do the same for the phi's, but if you divide this by V and take the V limit, you get what are the thermodynamic potential that are used at the deterministic level. Okay, now I want to speak about the last of the three classes of systems that I want to discuss, which are electronic circuits. You know, even though I would really like to move on the theory part of macroscopic thermo, I feel that it's also very important to give you examples of classes of systems where this applies. Otherwise, it's really abstract and in the air. And these circuits are remarkably relevant because they are used. We can actually model current CMOS transistors with this formalism. So this is Noel Freitas, is the guy who did really all the hard work, electronic circuits. He was a postdoc in my group during many years. He's now in Buenos Aires. Jean-Charles Delven was visiting in Luxembourg. And myself, PRX. I forgot to put the volume, the number. So you'll have to. It's stochastic thermodynamics of nonlinear electronic circuits. So he's now back in Buenos Aires, and interestingly, he's going to start a job in a company, Xtropy, that wants to actually build the transistors that we proposed in our papers. So it's a very nice story where, you know, we had our main motivation was that we wanted to start doing stochastic thermodynamics of information in realistic devices. This was COVID time, so Noel took it very seriously, and he read all the engineering literature on how to model CMOS devices. He understood that it was thermodynamically inconsistent, and he brought together stochastic thermo with the stochastic modeling of these devices in a thermodynamically consistent way. And so we could make energetic statements about CMOS transistors that are really the ones in our cell phones in the regime where they are very small and fluctuation play an important role. And we also evaluated that we've entered the latest technology of transistors is precisely entering the regimes where if you don't overpower these CMOS transistors, because currently they are overpowered. They work in a regime where you consume a lot of energy to avoid fluctuations, because the goal is precisely to avoid fluctuations. But if you don't overpower them, this is called the sub-threshold regime of this transistor, you have a lot of fluctuations, and you can actually use those transistors in the fluctuating mode. And one of the things that we propose is to use this as random number generators. And you know, currently in computers, when you generate a random number, you are using super accurate engineering that requires a lot of energy that then implements a pseudo-random number generator, which is completely absurd, rather than using the random noise that is really there for infinitely less amount of energy. So it fits into this big effort of computing with less power, because you may know that there's a lot of energy consumption associated to computing. So there's really a drive to search for new paradigm of computation that would use much less energy. And random number generation, they use it also in machine learning, so it plays a very important role. So if you can build architecture of these latest devices that are working in these fluctuating regimes, you could potentially do stochastic simulation for very cheap. And I think what caught the attention of the industry is the fact that while many proposals use technology that has to be put in place, this is actually with current existing CMOS technology, and the industry has like half a century of experience with that, and I think that's why they are quite interested about that. So to tell you that this really had implications, I don't know if it's going to really end up being used, but the company actually sent the order to design the chip that would actually do this random number generator. Okay, so back to the physics. This was kind of a little motivation. Imagine that this is the way to set the ground. Imagine that we have some conductors that are grounded, that are regulated. So it means that with respect to the ground, there's a battery fixing their voltage. And then there are other ones that are not regulated. An electron can hop between these conductors. So let's draw here another one that is regulated and another one that is not regulated. Okay? So let's call this one 4, this one 2, this one 3, this one 1. And how we're going to describe our n vector is essentially, I rename it Q because it's simply that you need to multiply by the elementary charge of the electron the number of electrons over each conductor. Okay, so we have a vector now, in this case, Q, no, it's correct. Q is going to be Q1, Q2, Q3, Q4. Okay, number of electrons on each conductor, charge on each conductor. Okay, whenever I say charge, you can think number of electrons. And we will have transitions between conductors. Let me label them A, B, C, and I give them an orientation that is arbitrary, like this. That sends them to K plus QE, so I always multiply by the elementary charge. The incidence matrix of the graph. So again, we have an incidence matrix. Let's write it for this graph. So we have A, B, C. We have conductor 1, 2, 3, 4. So the channel connecting 4 and 2 is labeled A. So it takes from 4, it puts in 2, and it doesn't affect 1 and 3. B takes from 3 and puts in 2. So it takes from 3 and puts in 2. And C takes from 2 and puts in 1. Yeah. Okay? Now, the charge is related to the potential in such a circuit. This is electrostatics via the Maxwell capacitance matrix. So this is called Maxwell capacitance matrix. It's symmetric. It contains mutual and self capacitance, and it is symmetric. This is known in electromagnetism. Now, you will see, of course, the analogy with chemistry, because our regulated conductors will play the role of the chemostated species, because there we fix the number of electrons, or we fix the potential more precisely. And the internal species are the internal conductor, the non-regulated conductors. And so I can rewrite this by specifying, I use Q for the non-regulated conductors and QR for the regulated one, okay? So non-regulated and regulated conductors. And so the charge is related to the voltage by these matrices. Since it's symmetric, this is the transpose, like this. And this is now the potential of the free conductors and the potential of the regulator conductors. And because we know that, as I said, what we are fixing here for the regulated conductors is their voltage, it's convenient to, you can simply write, Q is equal to C times V, Cm times Vr, and you isolate V. So you can write V is going to be equal to, you need to invert this matrix. Since they are symmetric, there's no problem. Minus C minus 1 Cm. And then here I leave QR. But I want, since QR acts on V and Vr, you can write it down explicitly. It's easy to see that here you should have Cm transpose Cm C minus 1. And here, sorry, I'm a bit, Cr minus Cm C minus 1 Cm. And that acts on, I should have written this, Q and Vr. So why this is important, it's to show you that this is the level of description that we will use, right, in terms of charges on the free conductors and the fixed potential of the regulated conductors. So these are the chemostats, the electrostats. These are the internal species. And the potential of the free conductors and the charge of the regulated conductors can be simply obtained by multiplying in a certain way those matrices to these guys. Okay, so if you know these two guys, you know these two guys, and so you know both voltage and charge of everything. So you're completely specified your system. Is this clear? You can check the algebra, it's really trivial. Now the energy, again, this is electrostatics. is 1/2 Q times V. And we do it first for the free conductors and then for the regulated conductors. Okay. It's a scalar product, so I can write it in both ways. Okay? And if I replace this inside here and this inside here, it's actually easy to see. So this here and this here. You have a cancellation and you get Q transpose C minus 1 Q plus 1/2 VR transpose CR minus CM Voilà. No, this is R. Okay, why do I want that? Because, as I said, we want to describe everything in terms of Q and V. So now we have the energy in terms of Q and V. Q and VR. Okay? And you can now also check that the difference between E, Q plus QE delta rho minus EQ is equal to, I don't do the algebra because it's really elementary, and since we are a bit short on time, I want to move on, but this is really arithmetics. There's nothing more than that. It is QE, QT, C minus 1 times this plus 1/2 QE square delta E transposed C minus 1 delta rho. Okay, and now, of course, you guess why I'm taking that difference. It's because of the local detail balance. But I still need to identify the non-conservative force. Let me do this here. Okay, because we have the difference of energy, but we know that we have regulated conductors which play the role of chemostats, so we will have an effect due to that. And here we use our physical sense for the following thing. So there's first an obvious work that the regulated reservoir will have to do to reset their voltage, right? Every time an electron is taken or removed from a regulated conductor, the picture that we gave with chemistry, the battery needs to restore the charge or remove it to set back the potential to VR, right? Because we're setting VR. So if an electron directly jumps on a regulated conductor, that's quite simple. The work that the regulated conductor will have to do in order to restore that charge is QV times that charge. Okay? So this is really, if a jump, the jump is happening on a regulated conductor. So if the electron comes or leaves the regulated conductors, this is the work that the battery needs to do to restore the voltage to its original state. But there are also induction effects, and this we can see from here, these kinds of terms, because even if an electron jumps on the non-regulator between here and here, they speak via electrostatic interactions, and so this will affect the charge on the regulated conductors, right? Here, you see it. So if I change Q, there's an effect that is going to act on my regulated conductors. And so these induced charges, based on these terms there in the matrix, is VR transposed, Cm transposed, C minus 1 times this. So that's the work that the battery needs to do to restore the charges on the conductor, but that's the induced charges due to a transition on the non-regulated conductors. Okay, so this term is really, you see, it's this one, because this is the charge on the regulator conductor generated by a change of charge on a free conductor. Okay, you see that this is the term, and that's why you get it back here. Okay, so again, briefly, the work that the battery needs to do to restore a charge, if it directly jumps on the regulated conductor, the work it needs to do to restore the potential if a change of charge is induced by a transfer of electron inside the conductor, between free conductors. Okay, so given that, we can go to the local detail balance. I will define, this is the heat. Until now, I never spoke about heat, but since there's entropic contribution here, conductors have no internal entropy, I can do this direct assignment. Let's not go into a long discussion about that. You can take it as a definition for RT log of RQ R minus rho Q plus QE delta rho. Okay, this is our local detail balance. It's also equal to minus delta Q minus rho. It's always useful to have that identity. Q plus delta rho like this. Minus, minus, yes. And this is now the change of energy. Actually, if you allow me to spare, do I do it? Let me say, so I don't have to rewrite it. It's the change of energy minus this work term that we evaluated along rho. Okay, you remember, change of energy minus work. This is heat. But now there's a subtle point, which is that actually this is not fully, the W is not fully non-conservative. There's a conservative part into it, and I will now show you. I know that I can actually, I think I need to move. Yeah, let me try to keep it for the moment. So I introduce phi of Q as E of Q minus the induced, the work that the battery needs to do for the induced charges, to restore the charges. Okay? So that part I take in. And why can I claim that it's conservative? Well, this you can check, and I leave it to you as an exercise. If you take the gradient of phi of Q, you recover V. Okay? So this part is really the conservative part, because you recover the potential, the same V, this one. So if you take this gradient of the potential, you recover this V as given here. So that's indeed a conservative part. And as a result, the local detail balance, I will continue it here. I can write it now as delta phi. So phi Q plus QE delta rho minus phi Q plus the remaining work, that is the one, plus because it's the minus. The remaining, the work done by the battery to restore the charges that directly are transferred to the regulated conductors. Okay? You got the general idea. So you see we're back to a local detail balance in terms of energy differences. We had to work a little bit because there's this subtlety of, in the work, there's a conservative part and a non-conservative part. But we're back to a picture. We have a potential describing the energetics of our system. Indeed, if you take the gradient, you get the potential. And the dissipative part, that is what the batteries have to do to restore electrons in the system. For this class of systems, I will not do it explicitly, but one can define an elementary voltage, that is the elementary charge, over a characteristic capacity of the system. And the macroscopic limit is actually corresponding to V equals 0. So if you want the big V that we will use for macroscopic limit, in this case is 1 over VE, and it also corresponds to the capacitance becoming very large. Okay, so typically circuits with a large capacitance will have large numbers of electrons, and the discrete nature of the charges will show up when the device becomes very small, because the capacitance is directly linked to the geometry of the device. And when the device becomes very small, the capacitance becomes very small, and this is what happened in these modern transistors. And the discreteness of the electrons starts playing an important role. Okay, and the characteristic voltage associated to this discreteness is this elementary voltage. Okay, what I didn't give you yet, how am I doing with time? I have 20 minutes. I need to make a choice now. I think it's more consistent if I finish with the applications, and then I will do things on slide tomorrow for the macroscopic limit. Because there's one more thing that I need to tell you here. You know, for chemistry, we saw it's mass action law that gives you the rates. And these rates give you local detail balance. For the Potts model, I argued that Glauber rates, Arrhenius rates all satisfy local detail balance. But here I didn't tell you how to get the rates yet, okay? So we know how local detail balance should look like, so we know what the rates should satisfy in order to be thermodynamically consistent. But an important achievement of Nawel is that he showed how to, from the IV characteristics of a channel, construct, using a B. Poisson model, the rates that describe the device. So I will spend, I think, the rest of the time on this to give you an idea of how that works, because it's important. I will not show it on concrete examples, diodes, tunneling junction, CMOS. I will give you the general idea. And then tomorrow I will also show you some practical applications. So the idea is the following. If I put, this is the notion of an IV. If I put a channel, so the channel, think of it as this thing, right? It's a conducting, it can be tunneling, so it doesn't need to be but here, but it's a piece, an object across which the electron will go. So this is rho, and this is a gated conductor. The battery is here simply to say that I apply a voltage V on the two sides of that channel. And I can get the IV characteristic of that channel. I should, more importantly, I should first say that that channel is modeled by a B. Poisson process. So it means that I have a rate for electrons to hop this way and a rate for electrons hopping that way that will depend on V. Okay? And because of this Poisson model, the IV, which is the current is simply the charge multiplied by the difference between the forward rate and the backward rate. Okay? And this is something you can measure in experiments. You apply a voltage, you measure the current, the average current through your junction. But then you also know that local detail balance needs to hold, okay? And so you know that lambda plus over lambda minus should be beta Q E V, because now we have a battery directly acting on the system. So this is the non-conservative force that transfer electron directly from one side to the other. And this means that I can rewrite this as QE. I factorize lambda plus, for instance. And then, as a result, I have 1 minus the ratio. And the ratio, due to local detail balance, is given by e to the minus beta QE V. And so it means that with the IV and the local detail balance, plus the assumption of B. Poisson process, this is not a minor assumption because not all devices can be modeled by such a B. Poisson process. Regular ohmic resistance cannot, but tunnel junction, diodes, CMOS transistor in subthreshold regime. I don't enter the specifics, but it's typically devices that have a shot noise behavior that can be modeled by this B-Poisson process. So in that case, with this assumption of B-Poisson, the IV plus the local detail balance, we have a way to construct the rates. Okay? And those rates now, of course, here they are in between two fixed conductors. But we need to put them back into our device. So one thing is to get the rates. This is how to get them. Another thing is to put them, to have the rates in the circuit. And here the trick is the following one. I will let you do the algebra. If you take this choice, plus minus rho of Q divided by QE, so that this has the dimension of a charge. Okay, so because this has to do with the, if you divide it by QE, with the difference of charge between before and after an electron has crossed, has made a certain transition in your circuit. So now you replace in the rate that you obtain the dependence in V by that difference, and you can check that as a result, actually I should have it here. Yes, you can check that as a result, this, you will have to use this property here. No, plus divided by minus so now with those rates using this property and this property, you can check that you recover delta Q rho of Q. Okay? So that's a way to construct your rates in such a way from these IV characteristics in such a way that you can use them to model the electron transport in your system. Good. In the remaining time, what I will do is briefly show you that you can, because this is still a picture that is very abstract. I mean, abstract in the sense that how does this connect to something that looks like a circuit that you see in electronics. So just to give you the kind of picture, it's like that. So this is an inverter done with CMOS transistor, PMOS and CMOS. Obviously, I just want to give you an idea here. I'm not, initially I was planning to go into the details, but we'll have no time for that. So this is the way that a PMOS is represented, and this is the way like an NMOS is represented. So this is the PMOS, like this. This is the NMOS. So P, N. So you have a VDD, an applied voltage here and here. And here you have V1. So this is my free conductor. And this is my input. So in this picture, how many conductors do I have? think of it as pieces of metal. I have this piece of metal, this piece of metal, this one, and this one. Okay, so the way to connect a picture like that to a picture like that is to have something like this in mind. This is now a conductor that is set at VDD. This is my free conductor. This is another conductor that is set as at VSS. And this is a conductor here that is set at V2. And now, via these PMOS, NMOS transistor, what I will have is electrons going through these devices, so from here to here to here. So what's happening here is that we have two channels, the P channel and the N channel. And we have a capacitive coupling. This is actually what controls the gate voltage of a transistor, because this is the gate. It's like the controller of which door here is open or closed. That is capacitively coupled. So you assign a capacity to this and to this, and a capacity here. But these, I should be careful, these are not wires. Huh? These are, I put little dots. This is just symbolically showing that there's a capacitance between these guys. Voila. And this is what I call V. Okay? And so these are the processes IP. This is the process IN. You get the idea? The pieces of the circuits are pieces of metals. They are treated as conductors. And these devices in the subthreshold regime, so this is when this guy is not too strong compared to the thermal voltage, so that there are still thermal fluctuation going on. You can describe it as a Bipoisson process because it displays shot noise. And to give you, now I'm entering a mode of more giving you a feeling. This is not, I skip all the detail analysis. But this is still, can be almost, kind of treated analytically, this model, because it's quite simple. In terms of Markov chain, what we have are, imagine that this is the ladder of V. And what we have is two jump processes. So we can jump between one state and another via a P process or via N process. And so it's like a Markov chain on a line, which can be solved analytically. And I go back to my original edges. You remember why we need to specify edges. It's central here to know, to not lump these things, because one is associated to this process, the other one to this process. So if you want to do the energetics, you need to specify which one is which one. And so that's the Markov process, and the rates are constructed by using the IV of these inverters, using the strategy I told you. It's by construction thermodynamically consistent. And so you know these rates, forward and backward rate along all the edges, and you can solve the problem. The kind of things that you get, let me first give you the intuitive idea of what an inverter is doing. So if this is V2, the input, this is 0, the average V2. It's an inverter because when, let me draw it like this. When the input is up, what's going to, yeah, this is V. What's going to happen to this V here? So up, this one goes down. Okay? So it's like a knot. I say yes, the output says no. I say no, the output says yes. So it's a NOT gate. And it's used as a NOT gate. And depending on the property of the inverter and the powering, you can control the slope. And you can also, you can see that if V2 no, V2 is actually not an average. This is the average, sorry. This is the input. If V2 is 0, you will always have a distribution. Now I'm plotting P, the probability distribution of the charges on the free conductors. So when V is 0, you always get something that is centered around 0. And if you increase V, so at VDD equals 0, you would get this. If you increase the powering, VDD, here implicitly I took VSS equal minus VDD. So the powering is, VDD is really the difference of potential between here and here. That's actually how the device is powered. So without changing the gate, you always get 0. But if you start changing V2, okay, it's V2 over VDD is a certain number, minus 0.01. Then you start having something that moves on one side. And if you increase V2, you can really get something that is very peaked here, okay? And that's when it works as an inverter, because the probability distribution is going to be centered here. So you can study probabilistically. Here I only plotted the average, but here I looked at the probability distribution. Okay, I'm giving you only a flavor of what is happening. Or maybe also the intuitive picture. So I like to draw it like this, otherwise I always forget it. So when V2 goes up, P closes. So the idea, you can schematically, this is the door that gets closed. And when V2 goes down, this is the door that gets closed. And so the intuition is that when V2 goes up, this door gets closed, this one gets opened. So this guy, this guy will equilibrate with this guy because this door is closed, right? So these electrons will equilibrate with these guys. When this door is closed, these guys will equilibrate with these guys. So that's more or less the intuitive picture of what is happening. Okay, I still have 2 minutes. So now, just for the fun of it, this is a CMOS memory. This is used in your cell phone. It's actually 2 inverters coupled in the following way. So this is a P1, this is a N1. Wait. Yeah, so I'm trying to go fast, not plot the detail, but then I confuse myself. Tac, tac, and tac. And here I need to give a sense of the direction. So this guy is like this, and this guy is like this. So the idea is the following, and this one is a P and this one is a n. So this is V1, this is V2. Now I have 2 degrees of freedom. These ones are still fixed, VDD. So it's still powered. Okay, these are regulated conductors. These V1 and V2 are free. So I have 2 degrees of freedom now, 2 stochastic variables. And the logic is the following. Yes, in the sense of if I say yes, the output says no, and this says yes. So it's a stable state. Yes, no, yes. Okay? Because no as input is yes as output, so that's a stable state. Another stable state is no, yes, no. That's just to tell you that it should not surprise you too much that when the device is powered, it's very important that it's powered. If it's not powered, it doesn't happen. This is a memory for the following reason. The probability distribution, so this is P of V1, V2. I don't know why this is 0. Yeah, the 0 and the 0. It's going to be centered like that. I get a bistable state. So most of the probability is centered here and here. So I can use this to store information. This is a bit. If I have my probability here, it stays here. The potential is a kind. If I look at the potential along the diagonal, and you can get it analytically, you have a distribution that is like that. And for this, you need to power. If you don't power, you get something that is not able to store memory. So storing memory requires powering and requires dissipation. And you can study the error rates in these models and the dissipation of these models, how the error rate scales with the dissipation. And okay, you can, if you wire this in a different way, you can actually do a Maxwell demon with this also. So, because you know, it's this story of opening and closing doors. So you can use this device in the opposite direction in a way that if I apply a potential difference between here and here, electrons, they want to go this way. But this device is tuned in such a way that it measures when an electron, a fluctuation is going up or down, and accordingly closes the relevant door to invert the direction of the current. So you can make this work as a Maxwell demon, and you can even show that it continues to work at macroscopic scale, provided that your VDD scales with the size. So you need to increase the power to make your macroscopic Maxwell demon work. If you're interested in the Maxwell demon version, it's a PRL 129, and it's still with Noel. So I spent some time on that, but I think it was nonetheless useful to give you a sense of what you can do with these classes of systems, POTS, chemistry, electronics. Here they're really, on electronics and chemistry, I think they're very real application. I mean, even POTS has some application. So we now have all the ingredients. I hope I also motivated well the starting point where we have a description in terms of occupation, and there's a parameter that is an extensive parameter. And so tomorrow at a different pace, because this is going to be slides, we will show what we can say when we take the large V limit. But you should also already kind of not be surprised. I mean, there are a lot of, I wish I could have the time to go into the details. But since we know how to do thermodynamics for small number of particles, we have everything to still do thermodynamics when we take the macro limit. And so we will be able to do thermodynamics at the really infinite extensive limit where everything is deterministic. But we will also be able to look at macroscopic fluctuations. And so we have all the ingredients. It should be clear by now that we have all the ingredients to do thermodynamics out of equilibrium on these macroscopic systems that have relevance, practical relevance. Yeah.
Using this sort of macroscopic electronic devices.
You said micro or micro? Macroscope, yes.
So once this whatever
Yeah.
macroscopic devices, right?
No, well, this is the point. Okay, all this, of course, apply in the macroscopic limit, but there I will not teach anything to engineers. Because the macroscopic limit of this theory is actually circuit theory that engineers use.
Yeah, but no, when you want to apply it on this CMOS or whatever,
Yeah.
do you have to make this CMOS at sort of mesoscopic scales, or it's still, I mean, like in practice, it's okay to work with?
No, that's a very good question, and it's related to what I used my narrative as a motivation. So this relates really to the practical things happening in the industry, where processors are getting smaller and smaller, and they're reaching size where fluctuations become important. So the latest processors are in regime where these fluctuations are really important, okay? And so the engineers, they want ways to describe the stochasticity of these devices. But the way they were doing it, and it's related to what I'm going to say tomorrow, you need to keep thermodynamic consistency at the level of fluctuations. Otherwise, you can create Maxwell-Demons effects. You will have currents flowing against biases, etc. Because they simply take the macroscopic equations and they add Gaussian white noise to it. And this gives you bad results. And I will explain briefly why tomorrow. And I will explain why with our framework we can actually properly describe fluctuation in a way that is thermodynamically consistent. And so it's relevant at these small scales. When I mean small scales, maybe this is also important, people like Peccola, etc., in the fundamental physics side of things, people have played with devices which have quantum dots-like device, single electrons. And there, you apply directly stochastic thermodynamics. This latest CMOS transistor, I mean, they start to have fluctuations, but you're still in the range of many tens to hundreds of electrons. And so it's actually a regime where large deviation theory is actually very powerful. And that is another thing that with large deviation, you can do some calculations in literally half an hour, I mean, not even, that the engineers with this stochastic method they were running, it's the error rates, it's actually precisely this. To get the error rates here, they were running Gillespie simulation for months to get the error rates of these devices because they are interested in the error rates, right? Because you want to know if you store information here, what is the error rate that happens? Because if you wait too long, you will start to have errors. You don't want that. So the purpose for current, in the current paradigm is you avoid as much as you can to have transitions between these two states. So you power your system such that this is really high. And then to calculate this, because it's very rare, it's very hard for them. But using large deviation theory, you can calculate an instanton and you can have the escape rate in like, and this they find very interesting because these are things they are not used to. But what we say too is, okay, you can also use this, not overpower it in a regime where you can have fluctuations. And then you can start to have this is basically a random number generator between 0 and 1. And you can tune the statistics of your random number generator. And that's, since you need to go at very low power to have more, to decrease this barrier and to have a lot of hopping, you actually dissipate much less energy. Okay, this is the type of questions that Nawel usually answers because he has all the numbers in his head. I don't have them out of my head. You know, the numbers for the capacitance of these latest circuits, these are things that he has. Some of them are in the papers. You can look it up. But I don't have them out of my head like that. What are the numbers that you're interested in?
I mean, the error.
Oh, for engineering, the error rates that they want is the type of, they want like probabilities that over 10 years, it's like one over, you know, they really go to levels where the precision of current computer is amazing. But that comes with an energetic price. But this is their problem, if you want, also, because given that the device becomes smaller and smaller, you know, you need to overpower them more and more to counter these fluctuations effects. Thank you. Yes, so I am doing the tutorial today. Ah, okay, I didn't realize, but okay, yeah, I will be there. I will think about what to. And tomorrow the tutorials? No, I don't know. I'm asking to. Okay. Okay.